Moving forward to the next industry presentation on ASR innovation comes from End-to-End Deep Learning and Transfer Learning, presented by Mr. Mehul Patel, Vice President of Products at Deepgram. This session is brought to you by our gold partner Deepgram. Mr. Mehul will join us virtually today. Handing over the stage to Mr. Mehul.
As a quick intro, my name is Mehul Patel and I'm VP of Product at Deepgram. Here is a quick agenda. We'll start off with a quick review of what is end-to-end deep learning speech recognition, followed by stepwise improvements of the models. We'll then do comparison of various speech recognition solutions. And finally, we'll review how using transfer learning, new speech or language models can be developed faster than ever before. Let's begin by reviewing traditional speech learning recognition models. The traditional model consists of 4 main steps, which need to be processed in order. This model became popular around 40 years ago and is based on how a person might logically break down speech processing into manageable subprocesses. First comes removal of generic background noise, stripping out certain frequencies that are present in most electronic equipment. The audio is then cut into snippets of 10 to 80 milliseconds and fed into the acoustic model, which tries to identify individual sounds. In linguistics, these sounds are called phonemes. The phonemes are guessed using a probability distribution based on the characteristics of the audio. Next, in the pronunciation model, the phonemes are pieced together and most probable word is guessed, again using a probability distribution. Now you have a lattice of possible words as a function of time. Notice in both of these steps, the model generates many guesses for each sound and word. Later, it's going to discard all the candidate sounds and words that were not highest probability. This process is inefficient, or in computer science terms, lossy, because it generates and evaluates a huge number of possible guesses that it does not use in the final output. Finally, these word candidates need to be culled down to the most likely series of words that form a sentence. This is typically done with an n-gram model. The n-gram generates the probability of various candidate words being correct in the context of the words known to be immediately around them. An industry standard is to look at the 3 adjacent words, which is why you often hear this called a trigram model. For example, if you submit a recording of someone saying, "I'll see you there," the model will get to the last word and know there are several candidates for there. There mean different things. It'll then look at the 3 preceding words, "I'll see you," and try to guess the right version of there based on the context. Let's quickly review drawbacks. 1, it's fragile, as it tweaks in one layer cascade unpredictably into the others. It doesn't build context. The closest thing it has to context is the trigram model, but it doesn't have context from the broader conversation. When us humans think of context, it might include things said 5 minutes ago or even 20, 30 minutes ago. It's lossy, lots of data generated and discarded. This inefficiency makes it slow and increases the cost. It is made even more inefficient by the fact that this system is designed to run on CPUs, which process data sequentially. More on that in a few minutes. In the end, result is that solutions based on this technology are adequate for some general purpose, so personal use, but don't get the job done for business applications. The limitations of these models make them difficult to build and maintain, so they are one-size-fits-all products. You get one general model for a widely spoken accent and hope for the best. And this is not the future of speech, which, remember, needs to be flexible and personalized. Next, the hybrid models. They were developed in an effort to take advantage of machine learning within the architecture of the traditional method. And they do this by incorporating machine learning in a localized way within each of the 4 steps. So in the traditional method, the acoustic, pronunciation, and language layers are usually driven by statistical models that predate machine learning techniques, such as HMMs or hidden Markov models. In the hybrid method, these older statistical models are swapped out for neural networks that handle one or more of the stages in the process. Using neural networks usually results in somewhat higher accuracy and some gains in processing speed. Hybrid models try to build more context for the whole conversation by comparing n-gram candidates to a history of past n-gram outputs. This is known as a bake-off. Fundamentally, though, it's still the same process. It's built very limited context based on just a few adjacent words and stores those outcomes for reference. So what's the net impact of the hybrid model? While hybrid model can offer localized improvements over the traditional method, they do not fundamentally change the game. Hybrid models still implement the same serial 4-step process. Each step is interdependent with step before and after it. So small adjustment to one part of the process will cascade in unpredictable and disruptive ways into the other processes. These models are still lossy. They still generate a lot of guesses on sounds and words and discard a great deal of data as they finalize the transcript. This makes them slow. They're also labor intensive to customize and still are typically used for one-size-fits-all general models. Aside from Deepgram, these hybrid models are the industry standard. Google, AWS, and other major providers are all using this hybrid speech model. There are 2 reasons why these other companies haven't innovated away from this 40-year-old approach. First, these companies have been doing speech processing longer. So they invested heavily in legacy technology that would be expensive for them to replace now. And second, most of these companies aren't focused on business use cases. They build speech recognition first and foremost for consumer devices like Google Assistant and Amazon Alexa, where the audio is simpler, and so the older methods are good enough. If they can sell that same product to businesses, great, but that's not their main motivation. That's why, as a business, you get one-size-fits-all speech rec solution from them. It's not adapted to your audio and industry needs. It's not priced to scale. The product is simply not designed for business purpose. Next, Deepgram's innovation is that we developed the first and only speech processing system based on end-to-end deep learning with neural networks. A neural network is a computing system inspired by the configuration of cells in the brains of us humans. In our brains, signals are received by a neuron, processed, and then passed into other neurons for further processing. Those neural networks in our brains are the infrastructure that makes us so good at understanding language. So with that in mind, we use artificial neural networks, end-to-end, as the infrastructure for our speech solution. Our system works by feeding audio signals into the top layer of deep neural network. The system is called deep because we have many layers of neural networks that process audio data in a pipeline. Each layer brings us closer to the correct result. There are no steps in our model like the traditional method. This may make it less intuitive to you when you're looking at the system diagram, but it actually more closely resembles how language is processed in the human brain. So to start, an end-to-end deep learning model is created by training the system with real labeled audio. That is, a sample of audio paired with human labeled transcripts of the speech that the audio contains. Through training, the machine learning algorithm learns how to reproduce that human labeled transcript by developing its own internal set of rules that reproduce the correct output as often as possible. The game changer with machine learning is that the computer does this on its own. There is no painstaking hard-coded by humans required. Simply with exposure to real audio and the correct transcript, the system autonomously tests and iterates until it has its own set of rules for producing accurate results. Once deployed into production, the system draws on that huge bank of knowledge to identify the subtle speech pattern in any audio you submit to it. So let's look under the hood. The first layer of our deep neural networks are convolutional neural networks, or CNN. A CNN is a type of neural network specialized for spatial learning. What we do is we feed the CNN a visual representation of qualities of the audio. That visual representation is what you see in the lower left here, a graph of relative audio volumes at different frequencies over time. Because the CNN is a spatial learner, it looks for patterns in that visual representation. Those patterns allow the CNN to identify sounds and words with excellent accuracy. Next comes a series of recurrent neural networks, or RNNs, and a transformer. These layers are powerful sequence learners. They look at the context of the audio before and after a given word and find the best fit output based on that context. You can think of them as performing a similar function to the n-gram in the traditional method. However, you'll remember from that discussion that the n-gram typically looks at 3 words before and after the word in question. RNNs and transformers are not limited that way. They take in the context of the entire contents of the audio file. This makes the horizon for context gathering much wider. As for speeds and cost, our system uses GPUs or graphical processing units rather than CPUs, like the traditional method. GPUs were developed for high-performance computing, including video gaming, animation, and Bitcoin mining. Because they take advantage of parallel processing, these GPUs can run end-to-end deep learning systems at a very high speeds. Remember that the CPUs of the traditional and hybrid methods do sequential processing rather than parallel processing. The result? The end-to-end system is 200 times faster than the traditional method and over 100 times faster than the hybrid method. An end-to-end system is also more customizable because it learns from exposure to new data. It operates at a lower cost because it's less lossy. And finally, like a human brain, this system builds context for the whole conversation to improve accuracy overall. Next, I'll review a side-by-side comparison on the topic of how you might want to evaluate speech recognition solutions. For many of you, accuracy is highlighted as your top concern. Accuracy matters and is one of Deepgram's key strengths. But beyond the accuracy you see during the testing, the next question you should ask is whether the system is teachable and customizable for your unique needs. These qualities will further boost accuracy into the future. The traditional and hybrid methods only let you add a personal vocab list and hope for the best. Through Deepgram, you can train a custom model that is an exact fit for your audio that you want the system to understand. When it comes to how audio is processed, the traditional and hybrid methods both use a step-by-step serial process run on the CPUs instead of using parallel processing on GPUs. This greatly slows down their processing speeds. Parallel processing with GPUs allows you to process an hour of recorded audio in 30 seconds, and that's 120 times speed up. Computing resource requirements are also higher for the traditional and hybrid methods because of how much data these methods generate and discard during processing. Our method is more computationally efficient and therefore costs less to operate per audio hour. This is important for businesses because it's better price for scale. When it comes to continuous improvements on accuracy, machine learning on neural networks is the most efficient way to accelerate and automate improvements. We designed our system with end-to-end deep learning to take advantage of this, and are still the only end-to-end deep learning speech processing company. When we compare these three different methods, I hope it's clear why our method using the end-to-end deep learning has a huge advantage over the traditional and hybrid models. This is not accidental. Our solution is the result of design choices and investments we've been making for years in order to bring the next generation of speech recognition into reality. Next, I'll cover transfer learning. As we have reviewed by now, unlike most other speech recognition providers, our foundation is built on end-to-end deep learning. This allows us to be much more flexible and fast in developing new languages and different model architectures using transfer learning. Transfer learning in deep learning is when elements of a pre-trained model are reused in a new machine learning model. Since the two models are developed to perform similar tasks, generalized knowledge can be shared between them. It allows us to leverage a model developed for a language as the starting point for a model for a new language model. We can use transfer learning from existing models, train them with audio and text to create new models within weeks instead of months. Next, I would like to focus on the results you will benefit from the end-to-end learning and transfer learning. In the last 12 months, using end-to-end deep learning, we were able to redesign speech model architecture to create a significantly higher performing enhanced model. It also increased effective vocabulary. Together, this resulted in large improvements. To highlight just a couple of them, one, it resulted in 19% relative accuracy improvement. As you know, that's huge. And second, our new model has 31% relative accuracy over a big tech ASR provider. In other words, you can experience best in the industry accuracy out of the box. In addition to that, we were able to redesign speech models to more easily develop new languages. We used transfer learning to create new language models significantly faster and with higher accuracy. And our results illustrate that. We added 22 new language models within 1 year. Also, our accuracy tested significantly higher than other ASR providers. So in summary, the end-to-end deep learning approach is hugely flexible and easier to optimize than the traditional or hybrid speech recognition model. And using transfer learning, new speech or language models can be developed faster than ever before. You can try our language models at console.deepgram.com. There, you get $150 in free credits. Thank you for listening today. I'm really glad you could join us.